Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lessons, of course, we did talk about the strength of the magnetic field for a wire, for a coil, and of course, later on for solenoid as well. So let me just remind you the equations, how we can find the strength of the magnetic field. Then, of course, we will start with solving some questions. But before that, let me just remind you a few questions regarding that, so that you know how are we going to use these equations. Yeah, we said magnetic field strength is basically, or to find the magnitude of the magnetic field strength for each one of these, of course, we said for a wire is basically B equals to what? Equals to mu I. That is basically magnetic permeability. We said if it is air or space, we'll use mu naught. Okay, let's go back, and then divided by what? Divided by 2 pi d. This d was the distance for that. Okay, what about for a coil? Remember, we said for a coil, basically we use B equals to what? B equals, because we have numbers of turns, we use mu naught Ni, that is number of turns divided by 2r. And we said if, for example, diameter is given, of course, we can just use diameter instead of 2r. And then for a solenoid, later on, you will see that B equals to magnetic field strength equals to mu naught Ni over the length here. And of course, we could have, we can write this equation differently once we get into this. Regarding the direction for this, if it is a wire, we said we're going to use our right hand rule. For example, the current is upward here. Okay, we'll say our thumb, all right, is basically should be the same direction as the current, and we'll curl our fingers basically. Okay, so the curling of our finger, it determines the direction of the magnetic field or concentric circles around the wire. And of course, this will be the direction of the magnetic field. That is this, yeah? For the coil, we said, okay, let's say this is something for a coil. And if this is the direction of the current, we said we are basically going to align our fingers in the same direction as the current. Then, of course, our thumb points in the direction of the magnetic field. So if that is the case, the current goes in. So we can do this one here. So you can see the direction of the magnetic field is outward. So I can use, of course, points here regarding this, yeah? And that is if, for example, remember that is inside the coil, but outside the coil it is going to be into. So of course it's going to be something, a circle like this. It goes like this one here, and of course it forms a concentric circle, as you can say, all around the coil here. All right, then the next, if it is a solenoid, later on we're going to see that. Okay, so of course it's going to be something, let's say something like this. That is the case, we're going to draw something like this. That'll be a solenoid, by the way. Let's just make it this much. And then once again, here, we are, for this tool, we're going to do the same technique. Our finger should be in the same direction, or the direction of the current. Our thumb points the direction of the magnetic field, or north, you can say. So if the current is moving upward, we'll, of course, talk about this more once we talk about solenoid more, but just remember this. If that is the case, our hands should be in the same direction as current. So in this case, this is going to be north, and of course the other side is going to be south. Why? Because my thumb points in this direction here. Okay, so these are how we can find the magnitude and the direction for each one of the wire, a coil, and a solenoid as well. Let me write this one more time. So this would be for wire, and this is for coil, and of course this is for solenoid. All right, solenoid, my bad. Okay, let me rewrite this. Okay, solenoid. So these are basically for each one of these here. So we ended up at practice 5b here, because last time we did talk about this one. We said we have basically two magnetic fields. One of them is for the coil, basically, that is outward here, and for the wire it is inward. So these two, of course, were canceling one another out, you can say, but not completely, yeah, because the magnetic field for the coil were bigger. So of course we ended up with this much, and it was out of the page. Why? Because you can, if you do this one here, the magnetic field is out of the page. Okay, so let's go through question 1 in practice 5b here. So what do we have? It says calculate the magnitude of the magnetic field in the center of a circular coil. So the case that we have is coil. Okay, and then remember this. How many turns? We have 10, okay, turns. Okay, and then we have a radius of 10 centimeter, but can we use centimeter? The answer is no, okay? So let's fix this one too. I think it's on the other side, yes. Give me a second. All right, so moving on. What else do we have? We can move this one up a little. All right. So take a look. Always write the information that is given. Then, of course, you can apply whatever that or find whatever that they're asking for. So calculate the magnetic field at a center. So find B. Okay, let's say here's B. I don't know what is wrong. I think it's lacking a little bit. So circle a coil of 10 turns. So we can say N is basically equal to 10. It's worded a little. So let's remove this and rewrite it. Hopefully we can get it without any problem this time. Okay. Graphics. All right, I think it's all right. Good. Okay, so let's use blue again. So find the magnetic field. Okay, remember it says number of turns, so N is basically equals to 10. What else is given? The radius is 10 centimeter. Okay, and then current, that is I, is basically 20 amperes. Okay, and mu naught is basically 4 pi times 10 to the power negative 7. And here's the equation, that is Tesla meter over ampere here. So what are we trying to find? Try to find B, or the magnetic field strength for a coil here. So now take a look. We can say B for a coil. Remember, what was the equation? B equal to mu naught N times the current divided by 2 times the radius here. So do we have everything we need to find B? The answer is yes. We need, for example, mu naught. So mu naught is basically 4 pi times 10 to the power negative 7. Very good. What about N? That is number of turns. That is basically 10 turns, 10 times. What about the current? That is 20 amperes. What about the radius? I'll say 2 times the radius, but don't forget, the radius is in centimeter. If you convert it to meter, it's going to be 0.1, or just divided by 100, you'll get 0.1. So do the math, of course, you will find the answer. So B, magnetic field strength for that coil is equal to this much. And because it is B, that is basically in Tesla. So the answer is going to be what? 1.3 times 10 to the power negative 3 here. Okay, now take a look at the second question here. It says, an electric current traverses one loop of circular. So how many number of turns? We have 1. Why 1? Because it says one loop. So you can underline this word here. Let's solve this one as well. All right, these are basically the application of the equation, but I don't like to leave anything behind unless if I don't have enough time. Okay, so let's do it here. All right, so we have, it says one loop, that means N is equal to 1. It says diameter, by the way, we have diameter here. Let's use D small for diameter. Okay, that is 50 centimeter. Remember, if I convert this one to meter, it's going to be 0.5 meter. That is 1. Okay, calculate the intensity of the current if the magnitude of the magnetic field at the center of whatever. So find the current. Okay, what is the current? How about if I write the strength or magnetic field strength first? Okay, magnetic field strength, that is B, equals to what? Equals to 2 pi times 10 to the power negative 5 Tesla. And mu naught is also given. So let me not write mu naught for now. Okay, let's go back a little. That is for this, and says find what? Find the current. So let's find the current here. So once again, but guys, remember this. There's diameter given. I can find the radius, or I can keep it as it is. Why? Because we do know that radius equal to diameter over 2. So if you're doing this here, basically, then later on, under the equation, we have 2r, yeah? But 2r is the same as diameter. So we can either use the diameter, or we can convert it to radius, and then we say 2 times the radius. I think it is an extra job. So B equals 2, magnetic field strength, okay, equal to mu naught for coil, Ni over what? Over 2r. Remember, we said 2 pi equal to the diameter, so I can keep it as diameter. But we want the current, yeah? So you can rearrange the equation. We'll say current equals to what? I'll go with diameter, by the way. I'll use diameter instead of the radius. So I'll say B, that is magnetic field strength times the diameter divided by mu naught and then N, yeah? So now you have all you need to do, just plug in the numbers. So B is equal to 2 pi times 10 to the power negative 5. What about the diameter? We said convert it to meter, so it is 0.5, correct? Yes. Mu naught is basically 4 pi times 10 to the power negative, and then multiply by the number of turn, which is only 1 because it is a single loop. And of course, do the math, okay? I equals to this much current or ampere, and here we go. This would be the answer, which is 25 amperes. Okay, now a few Zhyar questions here says, which of the following equation used to calculate the intensity of the magnetic field, but remember, at the center of a circular coil. So we want magnetic field, or B for coil. Which one is B for coil? Take a look. Which one of them is more likely? Do we have this? No. Do we have mu n without a current? No, yeah? So do we have over just 2? No. So the correct answer, of course, it is A. B, the strength of the magnetic field strength equal to mu ni, or mu naught ni divided by 2 radius. Okay. Now, what about the second one here? It says the magnet of the magnetic field at the center of the current circular coil is inversely proportional to which one of the following? Now listen, guys, in order to answer this correctly, you'll have to write the equation, yeah? So, and how do we do this one? It says inversely proportional to which? You need to write the equation of the magnetic field first. B equals to, for coil, by the way, yeah? It says a coil. So for coil equal to mu naught ni over 2 times the radius. So those that are above the fraction, these are directly proportional. These are direct, okay? What about the ones that are under is basically called inverse, yeah? Okay, so now we can, or based on this, after you see the equation, you can tell and you can compare and tell which one is correct. It says number of turns, yeah? So number of turns is directly proportional to B, so incorrect, because we want inversely proportional. It says electric current. Do you see that? Electric current is also above the fraction, that is directly proportional, so incorrect. Radius of the coil, you can see that the radius is below the fraction, so this is inversely proportional. This is the correct answer. What about, it says both A and B, that is number of turns and electric, so these are, or electric current, these are both directly proportional, so option D is incorrect. The correct answer is C, which is the radius of the coil. What if they were saying the diameter of the coil? That would also be the same thing. Okay. It says the physicist Dash demonstrated that when brought near a current carrying wire, a compass needle is deflected from its usual south-north orientation. Which one of these scientists were they? Was it Faraday, was it Lenz, was it Oersted, or Newton? And of course you do know the answer, which was Oersted, yeah? Basically Oersted said that, or he noticed, or let's say when brought near a current carrying a wire, a compass would deflect, or you can say that it changed its direction. What about question 4 here? It says an electric traverses a one loop of circular coil of radius 25 centimeter. Calculate the intensity of the current if the magnet of the magnetic field of the center is this much here. So I'll do the equation, you plug in the numbers and tell which one of these is correct here. So we want the intensity of the current. So remember, it says for what? For coil. One loop. So N is 1 and it is for a coil. For a coil equals to, B equals to mu naught Ni over what? Over 2R. We want the current here. So the current equals to B times 2 times the radius divided by mu naught times N, yeah? So you are given these values. So plug in the numbers. You tell me which one of these would be correct in here. Okay, now another question which is also very interesting and very easy. You can easily grab 2 marks here, or you can collect 2 marks here. And that is basically this one here. How do we answer questions like this, guys? If you could write an equation to tell, to compare, you can do that. If not, whenever you're given magnets in direction, always draw the magnetic field lines. So this is basically north and this is south. Let's use blue perhaps. Okay, so if I want to know, what is the question here? It says, which of the compass needle orientation in the figure correctly describes the magnetic field, yeah? So if I want to do this, we do know that magnetic field goes from north to south, yes? So if that is the case, I'll do on both sides, yeah? Those needles that fall on the same line and point to the same direction, that means they are correct. They are showing the correct orientation. If not, they are incorrect. So if that is the case, I'll do this one too, yeah? You can see. And of course, you can draw different lines. That is totally fine. Now we can compare the direction of this tree here. So I think I hit this direction here. Let's use a smaller eraser and see the direction here. Okay, so take a look here. I can increase or add this more and more. Okay, So how about let's start with A. Is A correct, or is compass A showing the correct direction? The answer is yes. So keep A in mind, yeah? What about B here? You can see that B is also showing the correct direction, which is this way. That means B is also correct here. What about C? You can see that C is pointing upward. Okay, so I'll have to rewrite this to here. So we said A is correct, B is correct. What about C? You can see that the direction of C is upward. This is where the direction of the magnetic field here? No, so C is incorrect. What about D? Okay, D is pointing this way, where the direction of the magnetic field is this way, so D is also incorrect. So what are the correct, or which one of these compasses would show the correct direction? That is only A and B. So which one is only A and B? That is basically option B here, A and B. Okay, now how about question 6 says calculate the magnitude of the magnetic field at a point in the air at a distance of this much from a straight conducting wire. Don't forget, this is a wire, right, carrying a current of 10 ampere, knowing that mu naught is this much. Once again, use the equation for wire. What was the equation of the magnetic field for a wire? Was that mu naught? Do we have number of terms? No, it is a wire, yeah? So mu naught I over what? Over 2 pi d. So mu naught is given, okay, which is basically this much. Current is given, that is 10 ampere. Okay, 2 pi, that is a constant. What about the distance here? It says at a distance of 0.1 meter. So plug in these numbers, you'll find the value for B here. Okay, what about the last one here? It says when you break a magnet in half, how many poles does each piece have? We said whenever you break a magnet into two, each magnet will always have 3 poles, yeah? That is north and north and north, yeah? Now, whenever you break a magnet into two, every single piece, no matter how big or small, it will always have 2 poles, and that is north and south. So don't forget, we can never have 1 pole. It has to be 2 always. Okay, now take a look at this one here. It says 2 concentric circular coils. These diagrams are not exactly representing the situation here, but this is just to help you understand how it is done, yeah? These are more like a solenoid, you can say. But remember this, we have 2 coils. One of them is small, the other one is big. We insert basically, or these 2 coils, one of them is inside the other coil, just like this one here. So what happens when there is a current in one, let's say in the 2 coils here? Of course, what happens if the current is in the same direction or in opposite direction, yeah? So let's continue the question, reading the question. It says, 2 concentric circular coils lie in the same plane. So if I draw the correct situation here, that'll be, this is one of the coils, let's say here's the direction of the current, doesn't matter. And of course, we have another coil, let's say, and this is the other coil, okay? So concentric circle lie in the same plane, we can say. And of course, you can say, here's the direction, or one wire for the current to go in, and then the other one goes out, let's say. And the same thing here and there as well. Okay, so 2 coils, okay? Blue coil, let's call it, and then the red coil. Okay, so it says the inner coil, that means the red one here, okay, has 120 turns, okay? So this red one has 120 turns and a radius of 0.012 meter, okay, or 12 meter, and carries a current of 6 amperes, you can say. The outer coil, that would be the blue coil, okay, has a turn of, or you can say, has 150 turns, and its radius is 0.017. You can see the radius is bigger. What is the magnitude and the direction of the current in the outer coil such that the resultant magnetic field at the center is 0. By the way, for the magnetic field at the center to be 0, these 2 currents must be in the same, in opposite direction. Because if they are in opposite direction, then of course they cancel one another out, yeah? But let's solve and find the magnitude of the magnetic field strength for each, and then of course we can worry about the direction, and then we can tell what is the direction as well. Okay, so let's solve this one too. Keep it here. All right, so now let's write the information for each coil. So I can redraw the coils, by the way. So let's say this is, let me just make it nicer since we're doing it anyway. So this is one of the coils, that is, let's say, the outer one. And then we have, this time, okay, let's make this one bigger as well. Okay. Now, Okay, so this is, let's say, the outer coil. It doesn't matter which one is, for example, the current goes in or out, it doesn't matter at this point here. So let's say this one is going in and this one is going out. Okay, we're talking about current here, and this is current. Okay, so now we can write the information like more about each one of the coils, and then we can continue this. So let's say for the coil, the inner coil. So we're talking about the inner coil. Okay, we have number of turns, it is 120. That is 120 turns. Okay, that is N. And of course, we have a radius for inner. Okay, that is 0.012 meter. That is this. And then a current, we can say I for the inner, okay, is basically 6 amperes. Okay, what else do we have? It says the outer coil. Now we have the outer coil. Okay, for the outer coil, we have a number of turns which is 150. 150 turns. Okay, that is one. And then the radius R is 0.017 meter. See, it is bigger than this one. What else do we have? It says, what is the magnitude and direction of the current in the outer coil when the resultant magnetic field is let's say, center 0. So find the direction and the magnitude of the current in the outer coil. Okay. If magnetic field at the center is 0, we can say net magnetic field is 0. So now, in order to do this correctly, remember this, guys. So we can say the net magnetic field is 0. Let me write this one nicer. The net magnetic field at the center is 0. What does it mean? That means the magnetic field for the inner coil must be equal to the magnetic field of the outer coil, but of course in opposite direction. So if that is the case, let's write the equation for both, yeah? We do know that the magnitude of the magnetic field here, we can say the equation for coil, yeah? So that is mu naught Ni over what? Over 2 times the radius equals to mu naught Ni over 2 times the radius. But hey, don't forget, these are 2 different coils, yeah? So this is for inner, this is inner, this is inner, and this is for outer, yeah? And outer, of course. Now mu, we have it on both sides, so of course they cancel out because it is a constant. But can we say the radius also cancel out? No, because they have different radius. What about the number of turns? That is also different here. Okay, so now I can plug in numbers into the equation, yes? So we can say, let's use different colors. So now, for the inner coil, what is the number of turns? We said 120 multiplied by, what is the current there? The current is 6 amperes. All right, divided by 2 times the radius. What was the radius? It is 0.012, yeah? Is equal to. Okay, on the other side here, we have the number of turns for the outer coil. The number of turns was 150. 150 multiplied by I. Do we have I for the outer coil? No, so I'll just write I for the outer coil here. Okay, what about the radius? I'll say 2 times the radius. What is the radius? It is 0.017. 0.017. Okay, now do the math, okay? I will equal to, you can do it here perhaps, you can find I here will equal to something and ampere here. And of course now we can use a calculator to find the current here. But before, how about if I simplify this before we do that, yes? We can say 120 multiplied by 6 divided by, use your bracket, 2 times 0.0112. The answer will be 330,000 actually. So this is basically 30,000 we can say is equal to. We can say all this, yeah? That is basically 150I out 2 times 0.017. So once again, if you want to multiply, this goes under, this goes up, yeah? So I think I'll have to erase this one. It's too small, but we've done it. Okay, right, it's black. So I equals to here, if I rewrite it again, that is basically 30,000 multiplied by what? By 2 times 0.017. That is correct. This is 0. Okay, and then divided by 150. This is I for the outer coil here. Okay, so let's do this one. It's 30,000 multiplied by 2 multiplied by 0.017. That is basically 1020 divided by 150. The answer is going to be 6.8 here. So we can say the current for the outer coil is basically 6.8 amperes. And this is how you do it. But what about, that is for the magnitude, yeah? What about for the direction? Because the magnetic field at this point here, it is 0. So we do know that, we don't know which direction it is, whether if it is clockwise or counterclockwise, let's say, okay? But because the magnitude of the magnetic field is at the center of 0, so the direction of this current must be opposite to the direction of the inner coil here, okay? So once again, the direction of the current in the outer coil must be in opposite direction to the direction of the current in the inner coil. This is how they can cancel one another out. If they were in the same direction, they will be additive, so they will build or make a bigger magnetic field. So magnetic field strength at the center will not or would not be 0 in that case. So remember, here is the magnitude and here's the direction. So what did we do? Let's summarize this. Because the net magnetic field is 0, or strength is 0, so that means the magnetic field of the inner coil must be equal to the magnetic field of the outer coil. By writing their equation, cancelling out the parts that can cancel out, and then by plugging the numbers, knowing which one is unknown, then you rearrange the equation, then you can find the answer, and this is how you can do it, yeah? Very, very good. Okay, take a look at these Rosati questions. Perhaps we don't have enough time to do all of them, but you can choose one of the questions here, and of course, we'll do it. How about we choose, for example, question 3 here. Says, an electric current traverses one loop at the center of the circular coil of 10 turns. I think this is pretty obvious and pretty almost like the same as the ones that we've solved, except then for diameters 10, let's say over 10 pi over 10 meter, you can say. Okay, we'll do this one in a second. When 20 ampere passes through it, let's say, and that is the case. So let's solve this question here. That was question 2, yeah? I think I was trying to solve question 3 or 2. Let's do 2, Kak, it doesn't matter. All right, so let's bring this one here. Just write the equation, all right? And then try to know what are the given information, then hopefully you'll be able to do whatever that is, whatever you can find, whatever that is unknown. Okay. Now, so this is basically what we have. It says calculate the magnitude of the magnetic field. So B is unknown, basically, of the circular coil. So we have a coil, okay? Number of turns is basically 10 turns, yeah? Okay, and the diameter is, what do we have? The diameter is basically 10 or pi over 10 meter. Diameter, all right, so let's say diameter is pi over 10 meter. Okay. When we have a current of 20 ampere passes through it, yeah? And of course, mu naught is given as well. So now, if you want to find the magnitude of the magnetic field strength, just write the equation and plug in the numbers, yeah? But you might say, what is this number? That is just a number, yeah? And that's it. So mu naught Ni, that is for coil, divided by 2 times the radius. We said, if you're given diameter, you can just use the diameter instead of 2 times the radius, yeah? So I can rewrite this one here. I can say mu naught Ni, instead of 2 times the radius, I can just say the diameter. So now plug in the numbers, 4 pi times 10 to the power negative 7 times number of turns, that is 10, times the current that we have, it is 20 ampere, and then divided by the diameter, which is 10 or pi over 10, yeah? You can say this thing goes up, or whatever, or you can just do the math and that's it. All right, so let's just do it as it is. But before that, I think this is below. Let's make it up a little here. This is the diameter. Okay. So all you have to do, you can just, how about we simplify this to, yeah? And this 10, of course, it goes up. So instead of writing it this way, I'll just bring it up. So that is all that what you have left, yeah? 4 times 20, that is 80, yeah? Correct? 80 times 10, that is 800. 800 times 10 to the power negative 7, yeah? Did I do it correctly? That is 200. 200 times 4, that is 800. 800 times 10 to the power negative 7. 4 times 10 to the power negative 7 times 10 times 20 times another 10. So it's basically going to be magnetic field strength is going to be 0.008. And of course, we're going to convert this one to milli or something now. That is 3018. Okay, can you see this? I hope you do. Okay, so by the way, I can move this one here. I can say what? I can say 0.8 times 10 to the power 3 negative 3 milliampere. Yeah, that is one way I can say. But let me just compare my answer to what is given here. So we have, you can see here, yes, because if you move 3 like points or 3 digits here, 1, 2, 3, it becomes what? It becomes 0.8. How many times did I move? I moved 3 times, and that is basically to the right, or you can say I've changed a small number to big, so it becomes negative 3. Okay, that is basically what I have. But this negative here, you can, instead of this negative, you can say milli, yeah? I hope I said it correctly first time. So 0.8 times 10, not times 10, because we already have this 10, so we can say 0.8 millitesla. Milli, it means 10 to the power negative 3, and this would be the correct answer. And this is basically how it is done. Nothing more than this. Okay, now a new concept, not totally new because we went through this one before, but of course here we'll go through the detail of this. Okay, so what do we have? We have the magnetic field due to the direct current in a solenoid. What is the difference between a solenoid and a coil? We said earlier, or we've mentioned earlier, that if we have, let's say, a coil, that'll be something like this, yeah? So we have many turns of this, and then of course, let's say these are the wires, one of them goes in, let's say the direction of the current, then the other one will be out. That is basically a coil. But when it comes to a solenoid, we have something like a spring, but of course, like, you know, like, there was another name for that, yeah? It's like slinky spring, I think that's what it is, yeah? Or you can see what I'm drawing here. So this is basically, that is, depends on how well you want to draw this one here. And of course, this is what I have. So this is basically, you can call it solenoid. Okay, this is basically solenoid. And you see the difference between this and this. This is a coil, this is a solenoid. This is basically, we're talking about, or we have radius here. Okay, here we have, instead of the radius, you can say we have the length, yeah? Okay, so what would be the direction of the magnetic field here? I mean, if you want to find the direction, or before the direction, let's talk about the magnetic field strength here. We said B equals to mu naught N, okay, Ni over the length here, because we don't have the radius here. Okay, now in terms of the direction here, remember this. Always align your hand in the same direction as the current, then your thumb will always point north. If that is the case here, the current is going upward here, you can see. So I'll do this one. By the way, guys, always use the front of the coil. What do I mean? If this is a coil here, I can align my hand like this way, or I can do the other way, yes? I can, for example, do it, let's say if that is the case here, I can align my hand like this, but look at the direction of the current. So I can do it this way. That is the front of the coil, okay, or the solenoid, not the coil. And I can do it this way, because in front of the coil, the current is going upward. At the behind of the coil, the current is going, I keep saying coil, solenoid. So in front of the solenoid, the current is going upward, okay? And then, of course, if you curl your finger, you can see behind the solenoid, the current is moving or going downward here. But both ways gives you the same direction, or it gives you the direction of the magnetic field or the magnetic pull, let's say. But for you, right, to do this safely without making any mistakes, always put your hand in front of the coil. So if it is going upward, you can do this. If it is going downward, you can do this. Once again, always use the front side of the coil so that you can do it safely and correctly. Okay, so if that is the case, watch this. I'm using the front of the solenoid. I think I said coil again previously. Okay, so always use the front of the solenoid. So if this is the direction of the current, so this is going to be north here. And if this is north, this is south. But this would be the same as if we are using a magnet here, yeah? So if I draw some magnetic field lines here, let's use a different color for magnetic field. So the magnetic field, we know that they are going from north to south, yeah? They're going from north to south. But listen, inside the solenoid here, we have all these lines. These are almost parallel to one another, or you can say almost straight, yeah? So we can see here, these magnetic field lines are very close to one another inside the solenoid. And then, of course, they are less close compared to outer magnetic field. So if I place an object here at first time at point A, second time at point B, in which one of these locations the object will be pulled stronger? Of course, at point B here, because you can see the magnetic field lines are closer. That means stronger magnetic field. Here, less strong. So, of course, now based on this, we're going to go through some points which are very important for you to know these, okay, very well. But before that, if a wire is coiled into successive loops that touch one another, like you can see here, these wires, shown in figure 5.5, basically then that is a solenoid. So what is the definition of a solenoid? We can say it is a long helical wound coil of insulated wire. By the way, these wires must be insulated, and of course. Okay, so you can see here. Now describe the magnetic field of a solenoid. This is very, very important, guys. So the first point here, the field lines inside the solenoid point in the same direction here. That is, keep one of the key points here. So look, this is the north side of the solenoid, this is the south. You can see all these magnetic field lines, these are, all of them point in the same direction. That is one. So you can see the field lines point in the same direction and are nearly parallel. These are not 100% parallel, but you can say nearly, yes? If these are nearly parallel, that means, of course, a stronger magnetic field inside the solenoid. What about the second point here? By the way, you can say and are uniformly spaced, and of course they are closer together. And we've learned that the closer the magnetic field lines to one another, that means the stronger the magnetic field. That is point one. What about point B? It says the field inside the solenoid is strong and nearly uniform. So if I ask you a question, at which location the magnetic field is stronger? Is it somewhere out of the solenoid or inside the solenoid? Of course, inside the solenoid. Why? Because the magnetic field lines are nearly parallel, and of course there are too many magnetic field lines. This makes it stronger here. The field outside the solenoid is non-uniform, okay? Non-organized, you can say, and or you can say much weaker than the interior field. So the fields at the exterior, outside, is much weaker than the fields inside, because you can see the difference. Yeah? These are, the magnetic field lines are nearly uniform, nearly closely, you can say nearly parallel. So of course make it stronger compared to the magnetic field outside. So how do we remember regarding the direction? We said align your finger in the same direction as the current. Always use the front of the coil solenoid, and then of course your finger will always point north. So if that is the direction of the current, as you can see here, let's use this. If this is the direction of, if this is the direction of the current here, you can see it goes like this, it goes like this, you can see here, yeah? So if you align your finger in the same direction as the current, then you can see that this side must be north, or you can say the magnetic field line pointing this way, then the other side will be south. We have a study tip, which is also very important. It says the magnetic field of a solenoid can be increased by inserting an iron rod or core through the center of the coil here. What do we mean by this? I think take a look here. So this is a solenoid, yeah? If we insert an iron core into the solenoid, of course, this iron core itself also will be magnetized, and of course, this makes this magnetic field stronger here, or you can just say the magnetic field lines in this solenoid will be stronger, or generally just makes the magnetic field of this solenoid much stronger. And how can we do that? By inserting an iron core or rod into the solenoid. Regarding the magnitude, we've mentioned that. For the magnitude of the magnetic field of a solenoid, we use mu naught Ni over the length, okay? Okay, and of course we have this one, B is measured in Tesla, mu, we've said it before, that measures in Tesla, you can say Tesla meter over the ampere, yeah? Very good. What about the number of turns? That is in turns. Current measured in ampere, and length measured in meter, don't forget. Okay, now, what factors does the strength of a magnetic field of a solenoid depend on? Whenever it says what factor, always remember the equation, yeah? So just write the equation and you can tell us the factors. So we said the equation is basically B equals to mu naught Ni over the length, yeah? So it depends on the magnetic permeability, which is directly proportional. It depends on the number of turns, that is directly proportional. It depends on the current, that is directly proportional. It depends on the length of the solenoid, but inversely proportional with the magnetic field strength here. Okay, and of course you can see all that. Sometimes instead of saying the number of turn and length, you can combine these two and rewrite the equation like this. Mu naught, let's just combine these two together. But before that, let me ask you, would it be correct if I write it this way? Mu naught I, and then multiplied by N over L, yes? Would it be correct to write this equation this way? Mu naught times I multiplied by N over the length, yeah? If that is the case, we can call this one number of turns per unit length, yeah? Number of turns per unit length. Whenever something's divided, we say per unit, yeah? So number of turns per unit, the length here. That is also fine, yeah? Number of coils, you can say, or turns per unit length, which is directly proportional if we take these two together. Okay, and of course, we can say the type of the core. Let me not forget this. Like previously we've mentioned, we can increase the strength of the magnetic field of a solenoid by inserting an iron rod, or let's say, or a core, yeah? So by the type, what type of the core you're using, basically it affects the magnetic field strength of a solenoid. So don't forget point 4, that is also very important. The above equation can be written as this. Okay, we can also rewrite it as this one as well, yeah? This is just a matter of manipulating, let's say, with the factors that are given in the equation, nothing else. How do we determine the direction of the magnetic field, let's say, of a solenoid? Once again, remember this. We said for coil and solenoid, make sure that you always align your fingers in the direction of the current, your thumb points the direction of the magnetic field. So if that is the case, the current is moving this way, but remember this, yeah? Watch this. There's something you need to know here. Let's use blue, perhaps red, make it more obvious. So if that is the case, you can see this is the direction of the current. You can go like this, yeah? So now align your finger the same as in the direction of the current. So you can do this. So this side is going to be north, and then the other side is going to be south. And that's this simple. Like I said earlier, always use the front of the coil, yeah? So there is the direction of the current you can see here. So just align your hand in the same direction as the current. Then of course you can see that this side is north, the other side is south. That is another example, okay? So take a look. If that is the case here, you can, for example, align your hand in a way so that it aligns, let's say, for example, the direction of the current. If that is the case, you can see that the current is downward here, yeah? So do this. Always use the front side of the coil so that it makes it easier for you. All right, now there is one more thing here. Take a look. This is also a solenoid, and this is the direction of the current and all that, yeah? Now, what happens, watch this, what happens if I look at the one end of a solenoid? Let me see if I can get a paper, and then, of course, we'll talk about this one here. So basically, this is the end of the coil, yes? So if that is the coil, so if I look at the coil here, how does the current goes here? So let's get a paper, because this is also something interesting. All right. So basically, this is a solenoid. You can see the current is moving this way. Watch closely. The current is going like this, yeah? So if I keep doing this and I'll turn the coil here, what direction is the current moving? Is it clockwise or counterclockwise? Is it clockwise or counterclockwise? So I can do this. You can see that it is moving upward, yes? So here's moving this way, yeah? So that is basically the direction of the current is moving upward. So if I keep doing this, what is the direction? So if you look at one end of the solenoid, what is the direction of the current at this end when you look at it, yeah? That is basically, can we say it is clockwise? Yes. If that is clockwise, take a look. You can align your hand like this, yeah? If that is the case, remember this, we said always align your finger in the same direction as the current. So if that is the case, then north is basically into this. So you will see the back of my hand You don't see the thumb because the thumb is away. So the back of my hand is going to be south. Or you can say this end of the coil or the solenoid is basically south. So we can say whenever the current is moving clockwise, that end is basically, that end is what? Is the south pole, you can say, yeah? What about this end here? You can see that if we look at this end here, the current is moving this way, yeah? You can see that if that is the current, is going upward and then going like this. So if you look at this one here, you can see that the direction of the current is counterclockwise, true? So by looking at this end, it is clockwise. If you look at the other end, it is going upward, yeah? So you can see it's moving upward, yeah? That is the case. So if I turn this, you will see that this end is, or the direction of the current movement or flow is counterclockwise, my bad. If it is counterclockwise, opposite to the clock. So in this case, we can do that. Remember, if you align your hand like this counterclockwise, you will see that this direction or this end is basically north. So you can see here, when the direction of the current, if it is counterclockwise, it becomes north pole. And if it is clockwise, it becomes south pole. When do we use this analogy? That is if you can only see the end of the solenoid, not the front or the back of this, when only you can see the end. Or it doesn't matter. If it tells you that when you look at one of the end, if the current is moving clockwise, that is south, you can just align your hand just like the clock. So that means it becomes like this, yeah? So this is basically north. On the other side here, it becomes south. You can see that, yeah? If you align your hand like this, okay? So this side is north, the other side is south, okay? And if this is counterclockwise, you can see that basically this is north, and then